Our fourth speaker is Saket Saurabh. He's a theoretical computer scientist. He is my colleague at the Institute of Mathematical Sciences. Saket did his undergraduate studies also in Chennai, at the Chennai Mathematical Institute. He came to IMSC to do his PhD. His research focuses on designing efficient algorithms for a variety of problems, some of them very hard problems, coming from many different domains, trying to if such efficient algorithms could not be designed, trying to understand why that is so, proving that such algorithms do not exist, and so on. So he has looked at parameterized complexity, approximation algorithms, moderately exponential algorithms, graph theory, many more such areas. He has co-authored 2 books which are go-to texts in the area. Saket received Shanti Swarup Bhatnagar Prize for Science and Technology 2 years ago, 2021. He is a fellow of the Indian Academy of Sciences. He is a distinguished member of the Association of Computing Machinery. Today he is here to tell us more about the art and the math of puzzle solving.
I'm not used to giving this public talk, so excuse me for that. So the motivation for giving this talk was we were just flying someday and we bought this, I don't think you can see this book called Logic Games for Clever Kids. And so I was trying to do these puzzles with my son, and then they realized that actually they were doing some things which I was actually doing not too long ago, and then I thought maybe this is a good thing that I can share with all of you people. So for the best way to enjoy this talk is to solve the puzzles as we encounter them in the talk. So this talk has only 5 to 6 puzzles, and what they mean mathematically or in terms of computer science is what I will try to convey in this talk. Okay, so let me start. So first, let me talk about art of puzzle solving. We're not going to talk about maths of puzzle solving. And basically, just to do an example, I'm going to do Sudoku because that is what I put it in my abstract, that we will solve Sudoku. So let's do this. So this is the Sudoku, right? So I hope all of you know the games, is that you have to place 1 to 9 in each row, 1 to 9 in each column, and 1 to 9 in each block, right? And so that just means that these numbers cannot be repeated in the same column, same row, or in the same block, okay? So how do you go about solving puzzles, right? This is a Sudoku puzzle that I gave you, how will you go about solving it? You try to find a place where you could place some number. So here is the first way of doing it, right? If I did this, what does it mean? Do you find a place to put something which you know can only go there? So if you notice by this, I have tried to draw these red lines using the number 9, which tells us that 9 cannot be in that row, or 9 cannot be in that row. So if you look at the end block in the second row, that tells us there's a unique place where 9 can go, and that is at this place, right? Okay. So this is how we keep doing it, and we keep solving the puzzle. But as a computer scientist, I will like to look at it slightly differently and say, do you see any change in this puzzle after I put 9? So if you notice a little bit, number of empty squares reduced. So we made a progress on solving this puzzle by reducing the number of empty squares, right? So each time you fill something in this, something is happening to the puzzle is that more and more you solve, more and more number of empty squares gets reduced and reduced. So let's look at another example. Okay. Now if you notice, I did the same thing with number 4, which tells us that in the middle of my Sudoku, there's a unique place where 4 can go, right? 4 needs to go in that block, right? It cannot go in the first column, it cannot go in the second column, end column, and in the third column, 2 places are already taken. So there's only 1 place left, that is 4, so you place it here, okay? What happened? Number of empty squares reduced even further, right? So if I look at the Sudoku solving, and this is what I call data reduction, that you hear a lot in like whatever study you do, data reduction. So basically, what is data reduction? So data reduction for Sudoku is nothing but reduce the number of empty squares, okay? And what is reduction rules? It's a rules or method to to reduce the input data. Okay? So now I try to formulate some 2-3 basic rules by which you can solve most of the Sudoku puzzles. Okay, so this is my formulation. So here's my first reduction rules for Sudoku. I have given this name called locked candidate rule. Okay? So what do I mean by locked candidate rule? Like, it sounds fancy now, right? I have given it a name, but it is nothing but, I'll show you what I mean by locked candidates rule. So here's my puzzle again. What do I mean by candidates? By candidates, I mean, look at the empty squares. What are the possible numbers that can fit into that square? For example, if I look at this, right? If you look at this, 1, 4, how did I come to the fact that only 1, 4 can go here? If you notice this block, you try 1. 1 is not in that row. 1 is not in that block. 1 is not in that column. It means 1 is a potential thing that can go into that place. So 1 is a potential candidate that can go into the square. You can similarly do the same for 4. Okay? You do it again. You get 1, 4. You do it again for this square. You will see that both 4 and 6 are possible to go into that square. But if you do the same here for this, you notice that 1 cannot go, 2 cannot go, 3 cannot go in this because at that place, because 3 is in this place. Okay, 4 cannot go. Why 4 cannot go? Because 4 is here. 5 cannot go because 5 is here. 6 cannot go because it is in this block. 7 cannot go. Why 7 cannot go? Let's find the reason. 7 cannot go because 7 is above, right? And so 9 cannot go because 9 is already in the block. So the only number which is possible to go is 8. So that's my first reduction rule, which I call locked candidate. So now I'm going to tell that 8 is a locked candidate, right? So it's my reduction rule, which tells us that 8 is locked for that place, okay? Okay, so now I'm going to tell you another rule, which is called hidden singles, okay? And this is something which we have been already doing before. So let's look back to that, whatever situation we had, and what does this tell us? This tells us that 6 cannot be used at those places 1, 4 and 1, 4, right? But 6 needs to go in that block. So where will 6 go? There's only one place where 6 can go. It is that. So these are the kind of rules we'll call hidden singles rule. Okay? Okay, let's try one more. Now I'm doing with 7. Right? So if you notice, I did this with 7, so where will 7 go? 7 can go only at that place because that's the only thing which is left. So this is what I call a hidden single rule. Okay? And first, this is something which we all, when we end towards a Sudoku puzzle, we solve this, what is called unique missing labels. What is the unique missing labels? If you notice in this filled square, there's one block where there's only unique number that is missing in the left block. So you know what number is that. That is 4, so it's a unique label missing. So in any column, if you have filled 8 things, or in any row you have filled 8 things, or if you filled in any block 8 of things, then the unique thing which is missing, you fill that. So that is what I mean by unique missing label, so this is my missing label or missing integer reduction rule. So we saw 3 reduction rule for Sudoku. Rest, I'm not going to do it for you. You solve it at your own leisure. Okay? Okay, so basically, the idea that I want to propagate or want to convey is that you solve your favorite puzzles, and just before my talk, someone asked me something, and then I realized I should call it logical puzzle, not puzzles like wordies and something, but most of the logical puzzles, you can try to come up with your rule that reduces something which you have to do, and you have to come up with your reduction rules to reduce the data for your puzzle. And just to make my point even further, let me try to solve another puzzle, which is called planet matching. Okay? This is the second puzzle in this book. Okay? So what is this puzzle? So you have to draw, so you're given there are some shaded planets, and there are some unshaded planets. You have to draw either horizontal line or vertical line, and you have to assign each pair consists of one shaded and one unshaded planet, right? And lines cannot cross over the planet or nor each other. What I mean by this is the following. This is not allowed, okay? Because they are not horizontal or vertical lines. You cannot even cross it. This is also not allowed. So the only thing which is allowed is horizontal or vertical, and these lines cannot cross, and they are just horizontal or vertical. So I hope you understand the puzzle at least, right? Let's try to solve an instance of this puzzle and try to come up with some reduction rules to solve these puzzles. Okay, so if you notice here, this is this white guy, this white planet, because we are only talking about horizontal and vertical lines, either he can align with this shaded planet, or he can align with this unshaded planet, or he can align with this unshaded planet. But our rule says every planet must align itself with unshaded to shaded, shaded to unshaded. So the only possible option we have is this, because white, not allowed. So white-black is the only allowed lines we have to draw. So and now what happened? What did reduce? So number of unmatched planets decreased, right? So we did have some sort of data reduction. Okay. Once you fix the top one, this white one has no other choice but to be matched with this shaded planet, so you draw it. But if you look at the last one I have drawn, for the white one, there is a red line going, there's a shaded one going. So now you know that only one of them can go, that is white with the shaded one, so you apply that rule. So this is what I call it unique matching planet rule. So if there's a planet which has a unique partner, unique feasible partner, then you have to just match it, you apply that, you reduce the data, and keep going on solving the puzzle. Okay, so for example, look at the first star. This shaded planet at this point can only match to the one which is just above it, but the moment you do this, the other person has no choice, and he will go and match to the other guy. So what is a good thing about reduction rules is that initially, there are some things which you do not see. But once you apply, there's a lot of cascading effect that happens on the data, and eventually at the end, data will be either fully reduced, as happens in some of these puzzles, or it may not fully reduce, and in that case, we will try to say in which cases this does not happen, or what can we do to those. So you keep trying some of these things, and eventually, if you apply this just one rule called unique matching planet rule, right? If you apply, you are done with solving this puzzle, okay? So this is about my data reduction. What is data reduction? It's nothing but operations that reduces the input in some sense. Example for empty squares in Sudoku, or matched pairs in planet matching game, right? So what is art of puzzle solving is basically design, find, reduction rules, and reduce your data, right? So if you find one of these two rules, you can actually try one of these rules sequentially, and by the time you cannot apply them exhaustively, you will be done with your puzzle, okay? So art is to come up with these rules, right? That you can, it is never formalized, but you can formalize it the way I try to define for your favorite puzzle. Okay, so now let me ask the question, this reduction rule-based seems most natural way for solving puzzles. Can every puzzle be solved quickly using only these rules, or are there other ways to solve puzzles? And answer is, at least for logical puzzle, it's quite mixed, yes or no. So let me try to tell you why yes and why no, both, in the coming slides. And you know how do people create puzzles? The puzzles are created in a way, for a puzzle to be solvable, there should not be more than one solution. So there's a unique solution. Otherwise, it is very hard for a common person to come up and solve puzzles. So the way you see your puzzles in this Times of India or any books and this, they are largely have unique solution, and hence, this is why, because multiple solutions may lead to being stuck. So puzzles with unique solutions are somehow amenable to reduction rule. That is, again, it's based on my own empirical understanding of whatever I have seen. is that the puzzles, the way you see it or you know it, you can actually solve most of them by trying to derive some reduction rules or way to reduce data and apply them. And the reason is because they have unique solution. And what I mean by unique solution, I will give you in a minute. Do you see this puzzle? This is Sudoku. I have almost filled it. But if you notice, I can complete this puzzle in two ways. Look at the here and here, right? I know that in those two cells, 2 and 7 has to come. In the last two cells, again 2 and 7 has to come. But the moment you fix the 2 there, 7 gets fixed here, 2 gets fixed here. So that's one solution. You fix 7, everything gets. So it's a second solution. They don't give you such puzzles to solve. Okay? And if you really wanted to make a difficult puzzle, what will I do? That not at the end, because then you can see and you can do. In between of these puzzles, I will hide a place where you may have to make you have two choices, and actually both choices will lead you to solution, but you will still waste your time because you don't know, you will keep searching because you think that you are making a mistake. There should be a place where you should be applying just some unique thing, but actually it is not. So that is when they say difficulty level 8 and 9, then they actually start to give you one or two places where you might have to make choices. And this is how we make difficult and difficult and difficult puzzles. Okay? So I hope I have convinced you that why reduction rule-based rules are good enough to at least handle all your mathematical or logical puzzles. Okay. But now I have talked about some art of puzzle solving and puzzle making. So now let me tell you something about maths of puzzle solving. Okay? So for that, let me try to come up with a motivation, what I call yes-no problem puzzle solving. It's nothing but, so I'm asking you the same planet matching rule, but now I'm asking you, can you draw? Maybe you can draw, maybe you cannot draw. Maybe such a solution exists, maybe such a solution does not exist. Okay, so for example, for this, we can pair them up. So this is yes, there is a solution where shaded can be paired with unshaded, and they are horizontal, vertical, they do not cross, all the properties are satisfied. But let's look at another puzzle. Okay? So let's try to see how we can solve this problem. I call sanity rule. That's my first sanity rule. If I really want to pair shaded with unshaded, then better be they equal, no? Shaded planet and number of unshaded planets should be equal. And if you look at this picture, there's a 9 and there's a 9 there. So that's perfectly fine. But there is something called many to one rule. If you notice here, like for this planet, this is the only choice. For this planet, this is the only choice. So only one of them can get this black pair and pair. So if there are two unshaded pairs with one shaded planet, or vice versa, what should you say? No. We're done. Okay? So these puzzles can have both answers, yes and no. Like sometimes we may be able to solve the puzzle, sometimes we may not be able to solve the puzzle. Okay? But now you can ask, for these kind of puzzles, are reduction rules always sufficient? So we learned 3 reduction rules, right? Here, sanity rule, it applies, right? Number of shaded planet is number of unshaded planet. Many to one, it does not apply to this because for every black or shaded planet, there is 2. So if you notice, I cannot apply this reduction rule. So this also does not apply. Unique matching planet rule, no, I cannot apply because for every shaded region, there's a black and there's white. So I cannot apply any of the 3 rules that I have told you before. Then what is an answer? Right? I mean, so maybe we need something other than data reduction rules, right? So for many puzzles, data reduction rules is not enough. They're enough mostly, but here is one example of puzzle where it is not. But let me tell you how to solve this puzzle still. Okay? So this is called, I will reduce this to some planet matching to a normal matching planet. So what I do, just to solve, so if it is small, you can do this on your paper when you are trying to solve this. I name them. So the names are given to these planets. So shaded planets, unshaded planets gets the name A, B, C, D, E, F, G, and shaded gets 1, 2, 3, 4, 5, 6, 7. I make a separate box where I write A, B, C, D in 1, 1, 2, 3 in this. And now I try to see with whom A can match to either 1 or 2. These are the two possible options for him to match. How do I record this information? I record this information by drawing these two lines. A, which means A can match to 1 or A can match to 2. Similarly, B can match to either 1 or B can match to 5. Similarly, you look at propagate, propagate, propagate. You make this tiny picture on your this thing, and what you're asking, you want to match A, B, C, D to distinct numbers in 1, 2, 3, 4, 5, 6, 7 in this picture. So you cannot match 1 to, say, example 4 because there's no line between 1 and 4. So you have to choose this line such that the following happens. A is paired to some number, B is paired to some number, C is paired to some number, so on and so forth. Right? So you have reduced your planet matching to this simple matching planet. Of course, and here is one solution. A matches to 1, C matches to 2, B matches to 5, 3 matches to D. So whatever I picked up those, I have drawn into this. So what is an answer to this? Answer is yes. So I applied something which doesn't look like reduction rule. I also don't know how to solve those. But if you were drawing these things, what does unique matching rule mean? Unique matching rule means one of these A, B, C, D will have only one guy, so you have to pick him and you keep applying. But in this example, this does not apply. And this problem is called matching, and several of its variants are studied in literature. This is called stable marriages. There are set of pairs here, set of people here. They have preferences, and you are asking for a matching that is preferred and have some stability. It also, this kind of graphs also appears in something called kidney exchange. So there are donors, there are recipients, maybe those whose blood and this matches, you can this. Now you need to pair them up so that like one person cannot donate 2 kidney to 2 people. No? Right? So all I'm trying to tell you that the problem that we reduced to is a very, very well-studied problem in computer science. And so I'm not going to talk about how and what. That's not the scope of this talk. But all I can tell you that Gail Sepley won Nobel Prize in economics for coming with a solution to left puzzle. Okay? This was done in US for hospital residents, and they proposed a solution for which and these kind of things appears very naturally in resource allocation and things of this nature. Okay? So this was about matching. So all I wanted to convey is that for puzzles, reduction rules are great, but there are puzzles of other kinds where you might have to apply some other tricks. Okay, and just to put a point that matching is really important, here are so many books that have been written on this. Okay, so I was inspired by the book on the other side, but there are all kinds of books that is written. So take my point, it's nice, simple, and well-studied problem. Okay, so I hope I have conveyed some answer. Okay, so planet matching was different, but not difficult. Difficult, So I want to see some more different and difficult puzzles. And difficult means nothing but everybody takes a lot of time on those puzzles. That's what I mean by difficult. What is difficult? Not only you, anybody, if you give that puzzle, he or she is going to take so much amount of time. Okay? Okay. So I have my favorite puzzle, which I like. It's called two-coloring puzzle. So what is a two-coloring puzzle? So you see, this is a network is given. Your job is to color the vertices or these nodes red or blue, okay? Such that there is no line with both red or both blue. So if you look at any line, one is red, one is blue, okay? So this is the puzzle I want to do. So suppose I started with first guy being red, doesn't matter whether it's red or blue, but now do I have a choice? All the lines that are attached to this red better be blue. Okay, so let's apply this rule, propagate. Now that I have colored blue, all the neighbors are blue, they better be red. So I made them red, blue, red, blue. Hey, success, right? So in this puzzle, I started to be colored with red, I went to blue, And you have no choice. You propagate, you propagate, you propagate, right? So let's try another puzzle, okay? Same question, like it's just the same, different puzzle. So I start with the first guy. But no, I did the same thing, blue. Whoever could get red, I gave red. Whoever could get blue, I gave blue. But now, haha. So what is this? Is it that what we applied was wrong? Is there some other way to color this that I will get red and blue? Or is it that this puzzle itself cannot be colored red and blue, right? So we don't know. Our method did not tell us, our rule did not tell us. In fact, if you notice, there's something which is hidden here. This little cycle, this itself you cannot color with 2, right? You start with anywhere red, you will eventually end up this. And this is not anything about 5-length cycle, okay? Any odd length cycle will have a problem, okay? And maths tells you that any network puzzle where you have an odd length cycle, it cannot be colored with 2 colors, okay? But that's science, we'll leave it there. Okay? Okay. Okay. So what was the rule we had? So this is what I call reduction rule. Propagate the colors. Neighbors of red get blue color. Neighbors of blue get red color. That is the only rule we applied. And trust me, every 2 coloring puzzle, you apply this. If you succeed, great. If you don't succeed, you can very well say, no, this never works. It's a no. It cannot be colored with red and blue. So so this rule is correct. But it's not easy to prove that this rule, the reduction rule that you have applied, is correct, right? So this is why you need maths also, that, yeah, I have applied heuristic. It seems to work, but does it always work? Then the maths comes. You need proof. You need statements to prove that my reduction rule or my heuristic is completely correct, valid. Okay, so now let's try to solve another puzzle, the same thing, but it's called 3-coloring puzzle. Okay, so what is a 3-coloring puzzle? Now I want to color with red, blue, or green. Okay? Is the puzzle clear? It's the same thing, it's just that I have an extra color to do. Let's try red. Now, if I look at this guy, he has 2 choices. Either it can be colored with blue, or it can be colored with green. So let's just give one color. Similarly, this guy has 2 choices, either blue or green. Let's decide something. So I decide to give it green. Okay? Now, same thing, the other guy here had a choice of getting red or blue. I made some choice. I said, okay, red looks fine. But now you are seeing that unlike earlier puzzles, every time we have choices and we are making some arbitrary choices. Okay? But now, this one has no choice. He is supposed to get blue because one of his friend is green, other of his friend is red, so he better be blue. Similarly, the other guy gets fixed. He will get a color green. But now, again, on the top, we have a choices, so I decided to give, it had a choice between red and green. I decided to give red, some green, because then green had no choice because his friends were already blue and red. So whichever gets fixed, you use that color, red. Now the middle guy has to get what color? Red guy. Last one. So there is no way I can complete this. So is it because this cannot be completed? Or we had a lot of places to make choices, and we made maybe some wrong choices. So let's try again. Okay, so this time, remember, I gave this guy green. This time I decide to give it blue. Blue. I gave red, gave green, gets fixed, fixed, fixed. Now, the second one, it can be given red or green. I just decide to give red. But now I have a choice. I can give it to green and complete it. Right? So what happened? This puzzle was solvable. It's just that our choices were not optimal in the first time. So let's see. So 3-coloring puzzle had to make a decision and see the effect of decision much, much later. It's like life. One was right, one was wrong. For example, choose study mathematics or play cricket. When you were young, this is right? You decide to study maths. After a long time, you realize, like me, math is hard, should have studied computer science. Okay? Or you play cricket, hey, success. But it's not that easy to get success in cricket. So all I'm trying to communicate is that you make decision and you see its effect much, much later. It was just about one decision. Sometimes it's even worse. Candidate H or candidate R. You do something, and afterward, you have choices. Nuclear war or environmental disaster. I mean, either of the outcomes at this point is not nice. Right? So all I'm saying to you that you make some decision wrong, you reach at some stage, and every possible path from there leads only to no. But sometimes you make some decision and you end up at football or cricket, and whatever you do, you still succeed. So you make one decision, after that every path leads to success. Okay, lucky, unlucky. So what was there? So 3 coloring puzzle, we had to make many decisions. First one, we have to choose either color him green, blue, or red. Second one, again, should I color him green, red, or blue? Keep on doing it. So if you notice, this is the only math slide I have. For every vertex, I had 3 choices of green, blue, red, green, blue, red. So how many possibilities we have? 3 power n different colorings to try before we can reach whether it is colorable or not colorable. Okay. So let's try to solve this puzzle, not by us, but by computers, which are very fast. But they are really that fast? Let's see. You know how much computers can do in 1 second? Roughly 10 to the power 8 operations. As much as it's like 3.5 years of our time. They are as fast as this. Okay? So how tall is the tallest person in Chennai? You know how many people are there in Chennai? Roughly 65 lakhs or 6.5 million people. And this will take you 0.065 seconds. How tall is the tallest person in the world? There are roughly 8 billion people, so it will take you 80 seconds. Even to find the, tallest person in the whole country, this fast giant computer takes 80 seconds. Right? Okay. How bad is it? So just to tell you how bad it is, let's see, 2 coloring and 3 coloring. So suppose I give you 10 vertex puzzle, 20 vertex puzzle, 30 vertex puzzle, 1000 vertex puzzle, and even more. 10 nanoseconds, 20 nanoseconds, 30 nanoseconds, 10 microseconds, 1 second. That's exactly 10 to the power 8. Now imagine on the same, I ask him 3 coloring, it will take you 600 microsecond, 34 second, 30 is already 1 day. I mean, will you wait for such much time? Forget it. 1000 and beyond, forget it. This fast computer cannot do anything for you for this. Okay? So, what did I say? Red and blue coloring is an example of a good puzzle. Red and blue or green coloring is an example of a bad puzzle. And something which you actually don't know, Sudoku is a bad puzzle. You might think, because the reason why you were able to solve, because we make it easy, someone else solves for you and gives it to you so that you can do it nicely. But if I do a slight change here and there, it's a very hard puzzle. Okay, so this is my last game that we'll play, and then we'll end our talk. So puzzles with reduction rule that reduce with guarantee but does not solve. It will reduce some data. We can prove something about these rules, but we cannot guarantee that this puzzle will be solved. And this is the puzzle which all of you play. So this is called alien invasion puzzle. So there are n alien planes in the sky, and you have a fighter jet with K missiles in it. Okay, K missiles in it, and you have to destroy all alien planes with K shots. So if you take one shot, whichever plane are in the same line gets destroyed. Okay, so let's just take one example. So here are my alien planes. Okay, and I have to take them out with only 3 shots. Here comes, I take 1 shot, gone. Another, I take another shot, gone. Take the 3rd shot, gone. So I hope you have understood the game. So a sort can take all the planes which are in the same straight line. Okay? Victory. Now, here's my first reduction rule. So if a single sort destroys k plus 1 plane, use it. I will tell you why. And the number, because now you already have taken one sort. So how many sorts are left with you after that? One less, which is k minus 1. For example, look at this example. Right? Now you ask yourself, I only have 3 shots. If I don't take this sort, what will happen? If you notice, if you don't take these 4 planes which are in a line, then no sort can take more than 1. Anywhere else, if they come, it can only take 1 shot, not more than that. So any other sort can only take away 1 plane, right? So if you don't take this sort, then you need to have at least 4 shots, right? Geometry, right? So, I mean, if you only have 3 sorts, and you cannot do, and if you don't take this sort, then you need to use 4 sorts, then you better take this sort, no? So we decided to take this sort. What happened now? Now we are left with 2 sorts, but now if I don't take this sort, then these 3 planes needs at least 3 sorts to be taken. Great. So you take this. How much left? You have now 1 left, 1 shot, you go and take anywhere, it doesn't matter. Okay? So now I have shown to you, I have proved to you mathematically, if a single sort destroys k plus plane, use it and reduce your budget by 1. And here is a simple pigeonhole principle, right? And if no sort hits n by k planes, say can't win. If no sort can take there should be at least, not every sort can take strictly less than, say, 10 by 3, 10 by 3, 10 by 3. No, there should be one shot that takes at least 10 over 3 planes in one shot. Now let's put together. So we know that there is no shot that can take more than k planes, okay? And no shot can take more than n by, and there is no shots. So you know that there is one shot that must take n by k, but that n by k must be k, less than or equal to k. So how many planes are left? At most k square planes are left. K square alien plane. This is a mathematical proof. What did I show to you? I don't know how many of them are there, but I will apply these rules, and at the end, either I would have solved the problem or puzzle, or I can tell you, well, look, number of planes that are left is at most short to the power whole square. What's up? So now we are left with an instance with just k square planes, right? And you might ask, do you think we can be smarter? Can we do with something better? Well, there's a mathematical proof which says whatever we did for this alien plane, you cannot do better. You cannot come up with any reduction rule, however smarter you are, and reduce the number of planes by even 1. Right? So this is that kind. So you see, this is the maths. Okay, so what is the moral of this talk was? Pre-processing, silly, maybe smart, looking algorithms miraculously work. Okay? And you may think that what I was talking about, these puzzles and this kind of data reduction rules are all over the place, from big data to small data in machine learning, AI, and what all not. So what all things we do, we try to study which problems or puzzles have these kind of rules, which does not have. Can they always solve the problem? If not, can we bound the size? Is the upper bound tight? I don't know. So basically, all I do is art and math or puzzle solving. That's what I do for a living. And that's it. So conclusion is, effective and efficient processing is thriving. There are lots of nice results, lot of nice things that are left to explore. So please go explore. And here it is. Thank you very much for listening to me.
Thank you, Saket. I have a few questions for Saket, but I also have some more questions for the other speakers, so I can request you to come here while I start letting Saket field these questions. There's a question from somebody called Sarla. Are there useful science technology applications that have come out of the theory of some of the popular puzzles like Sudoku and so on?
Yes. like as I said, some of this art of solving puzzles or art of solving these reduction rules have been applied in industrial application of solving satisfiability, so it has found lots of applications. Also industrial applications of all these I was talking about, machine learning or all this, they are full of heuristics, and they're just heuristics the kind I was talking about. It's just that the situation or the instances change, but we apply something very similar.
There's another question from Parthiban. He asks, which is, in your opinion, a more productive exercise? Humans solving AI-generated puzzles versus AI solving human-generated puzzles?
AI solving human-generated puzzles. And the reason is, AI is generating what we asked him to generate, but we can generate much more than what AI can generate. So it will be fun how they tackle our problem.